Howard, and this will be the introduction for Lab 6. When an object is launched into the air, it follows a curved path called a projectile motion. This curved path happens because gravity constantly pulls the object downward while it continues to move forward at the same time. By separating the motion into horizontal and vertical components, we can better understand and predict how far and how high the object will go. In this lab, we study projectile motion using a mini launcher that shoots a steel ball at different angles. By measuring how far the ball travels and comparing it to the theoretical predictions, we can learn how to calculate important values such as velocity, time of flight, and range. This experiment also helps us see how physics equations can accurately describe real-world motion when air resistance is small. A good real-life example of projectile motion is seen when a soccer player kicks a ball across the field. The ball travels upward and forward, slows down as it reaches the highest point, and then falls back down due to gravity. Following the same type of curved path studied in this experiment, understanding projectile motion allows athletes, engineers, and scientists to predict and control the motion of any object launched through the air.
Hello, my name is Conrad and I'll be doing the materials. For this lab, we had the mini launcher, which was this right here, which has an adjustable protractor for setting launch angles. We have the steel ball, which is placed inside the launcher, which is the object being launched. We have the carbon paper, which will be used to mark the exact impact point of the ball on paper. We have the blank sheets of paper underneath the carbon paper for the landing area, so that way we can mark using the carbon paper. We have the tape to secure the papers on the floor, so that way they don't move during the trials. We have the meter sticks to measure the horizontal distance from the launcher to landing points. We have the protractor, which is built into the launcher to measure and set launch angles accurately. We have the lanyard or the pull cord, which allows us to trigger the launcher. And we have the cable, which is 1 meter high to ensure that the launcher is level and stable at the set height. We also use a notebook to record data and observations. This will be the first time we're using most of these, except for the meter stick and the table. Thank you.
Hi, my name is Gregorio Olivas.
And this is Kason Kelly.
And this is going to be the procedure. So for the first step, we set up the launcher. We placed the mini launcher on the table and made sure that it was on level. We set the launcher angle to 0 degrees horizontal using the protractor that was on the mini launcher. We then measured the height on the launcher from the floor. We taped the sheet of paper on the floor where the ball will land and placed carbon paper, the dark side down, on top of it. Next, to find the muzzle velocity, we loaded the steel ball into the launcher using the range of one click. Then we pulled the cord to fire the ball horizontally. The carbon paper would mark where the ball hit the paper. Then we repeated this 5 times to get consistent results, and then we measured this distance from the launcher to each mark and found the average distance. We used the formulas. Time is equals to square root of 2 times the initial y position divided by negative acceleration, which is gravity, and muzzle velocity. We calculated from final x position divided by time. Next, we then tested at different angles at 30 degrees, and then we used the muzzle velocity to find the horizontal and vertical velocity components. We used the formulas to calculate the initial velocity in each direction, which is horizontal equals muzzle times cosine theta, and vertical equals muzzle times sine theta. We calculated the time of flight and predicted distance using formulas. We drew a line on the sheet of paper to show where the ball should land and taped the paper to that spot.
In the data collection, we placed the carbon paper over the target page, firing the launcher 5 times at the same angle. We measured the average distance and percent error using the formulas provided in step 2. We repeated the experiment for other angles, 45 degrees, 60 degrees, and an extra angle that gave the farthest distance. We recorded all the data and calculations to be used for the conclusion. For the last portion, our TA would give us a target spot on the floor, and we would find the angle in which the mini launcher to hit the paper.
Hello, my name is Jorge Valdez. This is Lab 6 and I'm doing the data analysis. So for our experiment, we had to record our data for our ball launching experiment. So first we started off with gathering our Y initial, which was 98 centimeters or 0.98 meters, sorry. And our final position for our X, which was 1.47 meters. And then from that we calculated our time from this equation, which came out to be 0.447 seconds. And from that we got our X velocity, because there was only one plane when we were shooting straight on the 0 degree axis. And that came out to be 3.29 for our muzzle velocity. And then moving on from there, we have these equations, which we used a little bit farther up on step 6 to calculate our theoretical distances, and then to gather our experimental differences by taking different angles of the catapult thing. And then I calculated the times for each of them. So this one was for the 30 degrees, 45 degrees, and our 60 degrees. I calculated our distance final, like X distance. For the 30 degrees, the experimental came out to be 1.34 meters. For 45 degrees, it came out to be 1.1 meters. And for our 60 degrees, it came out to be 0.74. And for our theoretical, or for like our own one, which was 50 degrees, and that one came out to be 0.92 degrees. And then the actual experimentals came out to be 1.78, and then 1.56, 1.28, and 1.42. And then from that we calculated our errors, and then those are the errors that we got. I think that's it.
Hello, my name is Santiago Arras, and I'll be explaining going over the conclusion of lab number 6. So, lab number 6 was actually pretty chill, and it went smoothly overall. We figured out the muzzle velocity of the steel ball and used it to predict where it would land at different angles. And to say the least, like our results were good. They were close, not perfect to be honest, but the small errors probably came from things like factors like air resistance, maybe like spring recoil, the angle changes, or like maybe like human measuring mistakes, to be quite honest. I mean, none of the factors were super major, but they do add up at the end when it comes to our percentage errors and such. But I mean, to say the least, we were satisfied with our experimental outcomes and our theoretical outcomes. And so we could like take more trials. We can continue consistently to get more accurate results per se, but to be quite honest, there's only so much that we can do and that we can control that would really affect the outcome of this lab report. And so so in the end, the lab did a good job showing how projectile motion works, and how the math lines up with what actually is depicted in real life somewhat. But overall, it was really nice doing something a little different from previous experiments. Actually launching something and seeing the results made the concepts a lot more interesting and fun to work with. So yeah, it was definitely a good change of pace. But yeah, that's the conclusion for lab number 6. Thank you.
Hi, my name is Gregorio Olivas, and I will be going over the credits. Steph did the introduction, Kason did the procedure, Conrad did the materials, Jorge did the data analysis, and Santiago did the conclusion. I did the procedure and all of the editing. Thank you.